Good afternoon. Is the slide visible?
Yes, sir.
Yeah. Okay. So in the last class, we talked about naive-Bayes classifier, and we find that the conditional independence assumption for the naive-Bayes is not always true and in sometimes impractical. So as a solution, what we had discussed that this completely conditional independence is not that much practical. Again, sometimes if you say the it is fully dependent or the joint probability as a whole, that means that every variable are conditionally dependent. These also make the process mathematical intractable or computationally infeasible. So we have to think about some way that is in between, and thus we come to this today's topic called Bayesian network. So the Bayesian network is a kind of approach. First of all, we think it's a graphical approach, and this graph is basically tells us about the conditional independence or conditional dependence of some of the variables of consideration, not all the variables. Okay, let us try to understand. So what we have just said, that what is the problems of naive Bayes classified, that this assumption, okay, that assumption of conditional conditionally independent doesn't always hold. That often xi are not really conditionally independent. Okay, so that is the main logical disadvantage or logical limitation of the naive Bayes. Although surprisingly, naive Bayes do some right classification, even when not the right probability. So classification may be they do proper, but the corresponding probability is may not be that much correct due to this. So the important is that what if you say mathematically, our problem is this x1 dot 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 xn, and that is given y. So that is that means we try to find out that given this y, the level, what is the data distributions or data samples, you can say. Now this data sample is a multivariate, that means it is a now if it is a condition and it is a naive Bayes, we can say this is x1y, p is equal to this equal to p of x2y dot 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 p of xn. This is naive Bayes assumption. Okay, but then this is bit unrealistic or impractical image. So, but if you calculate this, on the other hand, this is a joint probability, joint conditional probability is mathematically intractable. So, but the solution is much restrictive and sometimes unrealistic. So this is our setting at this moment. What to do? So as I said in the first slide, the solution comes in form of Bayesian network. Okay, so no, this is the problem in hand. Now, what we really want to do, that just for example, if I try full independence, so this is naive. Naive base. And it is full dependence. Intractable. So, so if we say something in between, okay, so what we say, that how we go to in between, one assumption is that one statement we have to understand is called causal relation. Causal relationship is a that means sometimes some cause effect relationship. Okay, if you have uh, influenza, then you maybe have fever. So this kind of thing is called causal relationship, cause effect relationship. Okay, so one possible understanding for this kind of dependence or in between dependence independence, to find out the relations, causal relationship between the variables. Another thing that called specific conditional independence. So you can see that here our problem is basically this, that there is a x1 dot dot xn slash y. Now if this is the random variables, if we try to find out these variables, how these variable conditionally dependent or conditionally independent. So what I'm trying to say, that we're trying to find out some relationship between these random variables in form of this causal relationship, that means cause effect relationship. Just a second, just hold on 1 minute. Okay, sorry. So, what we are basically discussing that we try to find out something in between of this fully independence, that is the naive assumption, or the fully dependence. And these in between things in B can be addressed or can be represented using this causal relationship and the specific conditional independence. In today's talk, in today's class, we try to understand what do we mean by causal relationship and what are the specific conditional independence we are talking about. Another thing that we introduce a very interesting concept called belief networks. And this in belief network, we denote this causal relationship. Okay. So there is the different approaches. It's called belief network, that is actually DAG, the directed graphical model. Some Bayesian network that is called undirected graphical model. So today's class is important because in this particular class, we are try to understand the problem in a more broad viewpoint. Okay, I'll come one by one. First of all, what is the Bayesian network or Bayes networks? This is a directed type graphical model which represents the conditional independence relationship between different variables in the domain. So that we are trying to first understand that that is in maybe in this formation. Okay, so there is a some kind of uh, graphical model. So this may be a graph. Okay. So and you can see this is a directed graph. Okay, which represent the conditional independence relationship between the different variables that we'll see. Helps to get tractable inference when the all variables are not connected to each other. So now you sometimes you say that we can get this kind of occasions. Okay. So these two are not connected. So we interest to represent the dependence or independence between different variable in the domain of this. Okay, so there. So these domains, that's why you put not the condition. Now, how we are going to represent? Now, these are the, you can say the nodes. Okay, represent the variable. So these are the variables. And this arc is represent the relations between variables. Okay. And since there is a no arc in between, that is called lack of arcs represent the independence between the variables. Okay. Now, two things is important to understand here. One, do you mean by conditional independence? What do you mean by conditional independence? Another is causality. Some variable may, that I said earlier, some variable, just for example, that influenza cause fever. So this is some causal relationship. It causes. So cause effects of the others. If we represent the causality, we can get a more compact Bayesian network. However, the Bayesian network without causal, but always the Bayesian network has causality. It may not be have this cause-effect relationship, but the causal relationship is a such relationship that make the Bayesian network more compact. This description is a very overall description. When we'll see the actual example, you understand it very clearly. Now here you can see a Bayesian net example of a Bayesian network. Now you see there is some event or some variable. Let's say some of us basically late for work. Okay, so we are late for work. Now this late for work thing can be a cause. This is the cause of late for work. Maybe we wake up late. So these two variable, let's say if it is x and this is y, this y may be effect of the x. So there is some causal relationship. Now somebody is not wake up late, but still he may be late at work due to traffic jam. So this also. So traffic jam may be a reason for your late of work. So this is the kind of relations. Okay. Now traffic jam again may be due to some accident in some street, somewhere road in between, or traffic jam may be for rain. Okay. So it may be the rain cause traffic jam. Accident also cause traffic jam. These are the very kind of situations. Again, this accident may be due to rain. That also possible. Okay. Now, the thing is that since you are late at work, you are late for meeting. Or that is also meeting postponed it. That's why you are late at the meeting. So now these are the situation. These situations are a kind of cause-effect relationship or conditional dependence-independence relationship that is represented by a directed acyclic, or this is cyclic, but this is not exact the cyclic in this kind of acyclic graph. So now I just read out this. Arcs denote the causal relationship between the variables represented by the nodes. Now you can see these are the causal relationship. Directed acyclic graph, DAG, represent the nodes and the relationship between them. You said that what we said, that this is the relationship. Different conditional relationship can also be observed from this graph. So you can say. So just for example, what I said, the late wake up influence the late work. Again, the late for work influence the late for the meeting. So we can see late for the meeting, this may or may not be influenced by the note late wake up. Now, why this is the thing, that late for the meeting may be dependent by late wake up or by meeting postponed. Anything. One may not be late for work even if she is wake up late. So the note late wake up and the late for the meeting is not normally dependent. Is not normally independent, rather they are conditionally independent. You can see important. Note late wake up, this note, and the late for meeting in this two node is not normally independent because there is some relation between this. But if you say they are conditionally independent, if we know whether she is late for work, if now what I'm trying to say, you can say late for meeting doesn't depend on late wake up if he or she is not late for work. Is true or not? This node, late of meeting, late for meeting, sorry, doesn't depend on late wake up. This is another node. Okay, if he or she is not late at work. So you can see this particular node is somewhat dependent to this through this node. And we can say these two are conditionally independent if this node has a particular condition. That is called conditionally independent. If you know the whether C is a late forward. So that is important. And actually in this Bayes network kind of thing, we try to find out that how nodes are dependent. If you, one thing you have to be very careful that if you reduce the independence or conditional independence, better to say conditional dependence, then the mathematical or computational complexity become less. But if it is a too much sparse or too much uh, unrelated, then inference become very complicated. So it is much more impractical in nature. So you have to take it this hands. There is two things. Now another example here, same on the same diagram. They consider two nodes: the late wake up and accident. These two nodes normally seems independent, but given the node late for work is true. You see, look, true. They may be related. Now, if late wake up and accident, there should not be any dependence, okay? Because one did not wake up late, but still late at work, accident may be the cause of the late of work. So in that way, it is dependent. So in this node, this two node is that normally seems independent. There is no relation, but this late at work node implicitly make some dependence between these two. So it's called conditional dependency. Similar of meeting postponed and late for work. This node and this node, it is looks not that much dependent. They are normally independent, but may be related to the node late for meeting. Okay, so these are the way we have tried to understand this particular network. So if I say the Bayesian network is a graphical representation, okay? It's basically a graphical representation. We represent efficiently the joint probability distribution of the variables. Ultimately, we are doing this. That we are basically trying to do this. So any probability of conditional probability of interest can be computed if you know the full joint probability distribution, which is completely expensive. That is already said. And this Bayesian network, which is basically a reacted as I picked up, represent the joint probability more compactly, as we have seen in the last slide, especially if the graph doesn't have the too many edges. So here we are basically do a kind of something like that. So in this way, we basically do this network. What to as per our previous slides. So in the Bayesian network, nodes are represented by this x1 dot 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 xn. These are the nodes. Basically, these are the all different nodes. Arc depends on probabilistic dependence or independence among the variables. Said. Absent of arc denote the independence or conditional independence. Then this network structure is a DAG. This is the formal Bayesian network. At each node, a local probability table. Now, this is important. Each node table for a particular node in this chain, local probability table is maintained, which is called the conditional, can say CPT. It is called conditional probability table. So each node, how this particular node is conditionally dependent or independent, or some sort of cause-effect relationship holds of the other nodes. That table with each particular table, that table is related. So this is the formal description of a Bayesian network. The same picture is there. Now, so first of all, that how actually it helps. Okay. Yes. You see, the all the variables are Boolean. So these variables are actually Boolean variables for all the variables were Boolean variables. Okay. Now you see that the how the probability distribution is basically trying to take. If this is a Boolean variable, and if it is a naive base, so how many this possible combination to the power 7? Actually, to the 7 minus 1. That many combinations are there. Now, at the condition probability, that we have to keep the probability distribution of the node given the value of its parents. So what I'm trying to say, those node having no parents, that means this has a how many value that have. So there is no other parents node associated with it. So that means there is a one value associated with it. I'm coming why if it is a one, this just for late for working, this particular, no, better to say that I say some causal relationship we should take here. If you consider this only that two variable, that late for work, late wake up, this is one node, and that may be influence late for work. Okay. Now these two node. Now if we say this is the late, so that maybe x has some probability if he let this particular, let's say y is equal to 1. So this is one value, and this x y is equal to 0. So if it's a single parent, then we have two values associated with this. But if you have a this particular value is no parent, there is nothing is associated. So late wake up is taking the one value. So that's why they said now for the nodes having no parents can have only one value. A nodes having parents has a parent, one parent have two values. Now you see here in this here This particular node has one parents from name, so it is as a two values. This rainy day, it has one no parents as one values. Now traffic jam has two parents, accident and rainy day. So it's a 2 to the power 2 is equal to 4 values. Meeting postponed, 1 values. This is 4 values. This again 4 values. Okay, so we have completed how many total values? 1, 2, 3, 4, 8, 9, 9 and 8, 17. To total 17th entry, probability entry values is required to describe these relations. And if it is a naive base, it is what? I think 127. Okay. So you can see that is much compact representation. Okay. So we have to store 7 probability values for the table, whereas representing the fully connected Bayesian network, we have 2 to the power 7 minus 1 number of probability values. So we can compress the number of probabilities. So that what does this mean? The computational complexity is reduced by how much time? 17 by 127. That fraction we have reduced the computational complexity. Okay, it's almost 6 times, more than 6 times. Okay. Now you see how the Bayesian network is going to help. Okay. Now this in this Bayesian network, conditional probability table. So everything there is one CPT, condition probability table. With each node specify the conditional distribution for the variable given it immediate parents in the graph. So one thing is very important here, that each node is asserted to be conditionally independent to its non-descendant, okay, given its immediate parents. Okay. So that is also important, that it is conditionally independent with its non-descendant given its immediate parents. So for that reason, we can say late for meeting is independent of late wake up given this late for work. So that is basically saying this particular thing. Okay. Now, giving this kind of uh, Bayesian network or kind of a directed acyclic graph or a graphical model, whatever you can say, of a graphical model. How do you inference? So how do you infer something? So we can compute the posterior probabilities given evidence about some nodes. Okay, so we try to find out some posterior probabilities of that. For efficient computation, exploits the probabilistic conditional independence which is embedded in the belief network. So we can compute the probabilistic conditional independence which embedded in the belief network that we have seen. Unfortunately, the exact inference of probability in general on arbitrary Bayesian network is NP hard. So we cannot, even if this. So in theory, approximate techniques such as Monte Carlo methods, that also NP hard, but sometimes there's a useful, you can say, usage kind of thing. So efficient algorithms leverage the structure of the graph. So in this way, we can have some sort of way from these graphical models, we can infer something. The most of the cases, it is out of our scope of this course, because then we have to go for the graphical, how to do the graphical model. Now, given the Bayesian network with that we give you an example, that actually how what can be done with this Bayesian network? Okay. So what we can, first thing we can do the diagnosis. So what do we mean diagnosis? It's a the causal relationship. That means you say that COVID-19 is a cause, and what are the symptoms? Cough, breathing trouble, fever. These are the symptoms. Okay, that we can find out that what is the probability of COVID 19 given you have a cough. Okay, and what is the probability of COVID, same COVID 19, you have a some fever, something like that. Okay. So this is some diagnosis kind of thing. So this diagnosis can be done. Now we can say the prediction. What do you mean by this is called diagnosis? Okay. Now, given the cause that we have a COVID-19, okay, what is the probability that you got cough? So this is called prediction, that you have the COVID-19. Do you going to get these symptoms? May not be always true. So this is prediction. Okay. So some other thing, classification kind of thing. That classification means that that how you can say that these data are given. Okay. So can given the data, this data means is it that there is a some sort of data x i's and corresponding the class relationship is being given for I is equal to 1 2 dot m number of data is given in this way. That x may be a multidimensional thing. Okay. So if this is given data, so can we say that for a new x new, can we find what is the C? So what is the class C? That is the sum supervised classification. That also can be done to the this Bayesian net. Okay, so some decision making is also, if it's a causal relationship, that if there's a cough, that may be the symptoms of the COVID. So some other reason, the breathing trouble, there's some other reason. Maybe he's very kind of weak, or he's running or something, that is breathing trouble. So this kind of decision mapping, or this kind of decision tree kind of thing also possible. Okay. So in general, the structure of a graph, the conditional independence relation, how we basically, this conditional independence relation, how we going to say that this is the conditional probability, that is x xn or something, there is x3 between the, so this joint distribution is approximated using p of xi of these parents, because in the parents of xi, because you say that the parent, it only depends on the parents of the xi. Okay, so this is the graph structure kind of thing. Requires the graph is acyclic, no directed cycles. Two common component Bayesian network, the graph structure. This graph structure had, we can say that this is a structure kind of thing, and something like that. This kind of, and the numerical probabilities of that. Then see these CPTs actually at each graph. Okay, that is to find out this. Now here you can say that these probabilities are basically in this way. Just for example, the first example, if you say the first ABC, these are marginal independence. That means P of ABC, A comma B comma C. If they're independent, you can say P of A, P of B, or PB, and P of C. It is a naive construct. Okay. Now if you say that this A, the B depends from A. There is some cause of A, and C is basically depends on, but there is no relationship B and C. So there is a conditionally dependent independent effects. So how we can say that in this case, this is case one, this case two. So this is case one, case two. So that is how PABC is going to see. You see it very carefully. P is given A, what is the probability of B? You can say given A is parents. So this is what is the probability given A? What is the probability of C? That is, and there is a probability of A, there is nothing. So this is the basic probability of this particular joint probabilities, you can say in this way. So you can say this B and C are conditionally independent. Okay. In number three, you can see this traffic and late wake up, and it's a late for meeting. So we can say this PABC, how this is basically P is basically what is given, A and B is given. What is the of C? And where P and A and P and B are dependent. Okay. So you can explaining that maybe that this late meeting maybe due to traffic jam or due to late wake up. So this is the kind of explanations. Another very important, that is four. This is four. That is also, it's called Markov dependence. This Markov dependence is a kind of sequential nature. You can say it's a this is a timestamp T, this is T plus one, this is T plus two, and something like that. Okay. So here what you can see, P C belongs to B, P B belongs to A, and P of A. Okay. So that is also very interesting, that how these events are depends on the previous. So this is the way we trying to find out these joint probabilities using the Bayesian network or conditional independence. Now here you can say and understand is very easily that this particular thing here, what is that it is given this is the relationship in this way. Okay. So these values, there's y1, y2, y3, yn are conditionally independent. Because if see something happen, maybe that is reason for this, but this is not reason for that. So that is conditionally independent. Just for example, that we can say that it is a kind of thing, and that here this, if this kind of given that, so we always that these values are conditionally independent, and it is the naive of the naive naive assumption. Here is another very important thing. It's called hidden Markov model. And you can say observation YT are the conditionally independent of all other variables. This YT means Y1, Y2, Y3. YT means at the time instance T is equal to 1, T is equal to 1, and T is equal to 2, whether T is equal to 3, and T is equal to n, something like that. Independent, all are variables given ST. So the observation at the time T depends only on the current state ST. Okay. They are ST from first order Markov, but these are again, but this hidden state are interdependent. So okay, so here how to that S2 is basically the Y1 is basically S1. Sorry, so that is we can say that probability of y1 is on S1, probability of y2 is basically S1, S2, and probability of y3 S1, sorry, y3 being S1, S2, S3. But this is not observed. We observe only this. This is the hidden structure. So hidden state sequencer Markov observes YT conditionally independent of all other variable in ST, widely used in sequence learning and inference linear linear. So these are the way basically this particular thing. That you can say the ST is from first order Markov. So ST is basically ST1, ST1. So I write actually wrongly. This is the not the case actually. We have to write it in this way that P of S2 is depend on S1, P of S3 S2 S1, P of S, you can say Sn, you can say depend on S n minus 1 S n minus 2 dot 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 S1. So this is the Markov set. I'm sorry, this is right. So this is the actual way. But these are the hidden states, so we cannot observe it. So this is another way to do that. Another graphical model. So in summary, network structure is given in advance and all the variables are fully observable. This is one case, estimate the conditional probabilities. The network structure is given in advance, another case, but only some of the variables are observable in the training data, similar to the learning weights for hidden units on neural network, that gradient ascent kind of thing. A network structure is not known in advance. We heuristics as a constant based techniques to serve the potential structure. So these three are possible with the belief networks. That I believe. Okay. So we stop here today. Continue with another topic the next. Thank you.